Okay, thank you, Brian. And without further ado, we have our main presentation tonight. This is not a Kleenex box, as some might think. This is something magical, and we're going to hear all about it. We have Devon and Trevor. I don't recall which call sign is which, so I'm not even going to try. They were involved in a very special project. It's a unique thing that very few students have a chance, and I'm dying to find out what they did and how they did it. And with that, not much of an introduction there, but students at Arizona State University, and they're involved with the Phoenix Cubesat. So with that, Devon, Trevor, take it away.
Well, thank you for that very succinct introduction, Greg. Yeah, so I guess we'll have to start out with an introduction. So my name is Devon Batista. KM6MDG is the operative letter there. And it's both Trevor and I. So we're currently, I'll just introduce
Muted.
Quick. We are both pursuing, so we actually graduated with our bachelor's at Arizona State University in computer systems engineering. And we actually have our last class. Basically, we're enrolled this fall semester is our last class to get our master's in computer engineering. And so this project, for those of you that don't have any context, during our before we graduated with our bachelor's, this was a project that Trevor and I got the opportunity to work on. And in short, it's a 3U Cubesat that was Arizona State's first satellite, basically an object to be sent to space, as we'll get into. Before we move on, I'll let Trevor say some things about himself as well.
First, is my mic working? I know it wasn't before. It is? Okay, cool. Hello, everyone. As Devon mentioned, my name is Trevor, and yes, we are indeed brothers, twins, in fact. My call sign is KM6MDH. I forgot to note that here. And Devon and I actually have been in the same major and same classes basically our whole life. So he said 90% of what I was going to say. So we're both graduating this coming semester from ASU Masters. And this is an awesome project to be a part of. Learned a lot from it. So it's both exciting and there's a learning experience. So it's basically the culmination of college. What more can you get out of college? I'll give it back to Devon for the next slide. Oh, before we do that, the bottom URL there, the phoenixcubesat.asu.edu, if you want to find out any more about how the project, that is a great place to start. It's basically the introduction to what we did, and there's even links for amateur operators to interact with it there. So, yeah.
We'll get into that.
You control. Okay.
Yeah. Can anyone see can people see the slides, Trevor?
I can, so.
Okay, so I'll just go on.
Yeah, it looks great. Looking good.
Okay.
Thank you.
Cool. Thanks for the confirmation, Brian. All right, so just kind of an outline here. Well, let's kind of go over the overview of the project and the purpose, why we built the thing, and then the science behind the purpose. And those UHIs and LCZs are a part of that. We'll get into that. And then I'll kind of talk about the team and where Trevor and I kind of fit into the whole team structure, how we joined and what work we did on the project. Then I'll kind of discuss the overall design of the CubeSat. And then we'll get into what the launch was like, as well as how it was deployed from the ISS. And then finally, we'll just see how tell you where the project is now and how you can find out more about it. And so in the first section, the introduction, let's go over the overview here. And so this was the student flight research opportunity. It's actually funded by the NASA USIP program, which is the Undergraduate Student Instrument Project, as well as NASA Space Grant. And so the proposal for this project was actually submitted when Trevor and I were freshmen in November 2015. I actually remember going to a meeting of the Sun Devil Satellite Club, Sun Devil Satellite Laboratory Club. I was just a freshman, just kind of checking out the club, And I remember them talking about this actually, but I didn't really know too much, and I didn't really think to just pursue the project at the time. And so it's kind of funny to think about. We've kind of come full circle in that sense. And then after we submitted the proposal in 2015, it was accepted in 2016. And so this project was actually sponsored by this NASA program, as well as we've got a little bit of funding from JPL as well. And so this project was entirely voluntary, and there were mostly undergraduate students on this team, as you know, the S in USIP, or U in USIP, I should say. And so the primary objective of this project was to be an educational mission. You know, we're working with undergraduates here, so anything we do is going to be educational. And so we wanted to develop a functioning CubeSat, and this is a 3U CubeSat. I didn't put that in the slide, so it's a 3 unit, about the size of a shoebox. We wanted it to be capable of imaging the Earth in the infrared spectrum. And the secondary objective was to, this is kind of like the more sciencey one, was to study how city composition using local climate zones affect the surface urban heat island signature in various U.S. cities. And so I'll talk a bit more about what that means in the science section. And so this is a pioneering project for ASU. It was the first fully interdisciplinary and undergraduate-led initiative at the school, as well as the first satellite into space from ASU. We also have a ground station so Trevor and I actually helped install a large dish on top of our interdisciplinary science and technology building number 4 at the school, which is where we built the satellite to communicate. And we helped, there was also custom software at the ground station to help facilitate the communication. And here's a picture of the team, of the satellite team right after the proposal. Trevor and I aren't in here. This is from, I think Trevor said 2016. We actually joined the project later. A lot of the content I took from these slides was from our kind of proposal slides and stuff. And so there might be some gaping holes, but hopefully not too big. And so now I'll just talk a little bit about the science behind the satellite. And so an urban heat island is a phenomenon in which the temperature in a city there is much greater than the surrounding rural environment. It's linked to lower air quality as well as the rise in head exhaustion. And so if we kind of look at the diagram on the right, you can see, you know, like a more rural area has a lower temperature than the urban area. And this is caused by a lot of just heat absorption and retention, often by like the cinder blocks or like the concrete of the city. And so high energy rates occur often at high solar noon altitudes, as well as 2 to 3 hours after sunset. And so the satellite, as I mentioned in the secondary objective, aims to study these thermal distributions in cities at these times to understand how spatial patterns relate to high energy rates. And the way that does this is it looks at local climate zones, which is kind of a direct way to study urban heat islands. They basically allow us to classify a certain area depending on the building structure and materials to examine urban heat islands. And so that's kind of our objective, to just look at these local climate zones and assess how the urban heat island affects major cities. And so basically what our satellite does is it takes thermal imaging, as I mentioned earlier, infrared images of major cities, and basically sends those images down so our science team can examine them and look at how urban heat islands affect cities. So here's kind of like a visual of that. So the satellite's up there and kind of takes a picture of a certain area, a thermal image of a city, and then downlinks that to the ground station where our scientists can look at that image of major cities and do their research. And so the team. And so this is kind of our team structure. I don't see. Okay, there we are. All right. So The upper box is our, I'm not sure if that's visible, I'll just kind of read it. And so our principal investigators are Dr. Judd Bowman and Dr. Daniel Jacobs, or Danny and Judd, who are they're the ASU faculty who kind of helped us with this project, as well as our project manager, Sarah, who's often in the front of most of the pictures. And so we have a science team and then an engineering team. And so under the engineering team is a bunch of areas. Trevor and I, we worked in the software area. So we helped design the flight software for the satellite. There are other areas like the payload, thermal, attitude control, communications, mission operations, and then structures. And so Trevor and I, let's read it, we worked in the software area. And so how did we join? I'll let Trevor begin with this section because he actually joined before I did. And so go ahead, Trevor.
Yeah, so I joined, I think, yeah, so the whole story starts at the beginning of my junior year, which is before this became a capstone project, which is kind of the culmination project of an undergraduate student program. So in the beginning of my junior year, I heard about this project when a classmate, actually the software lead of the project, advertised it to the class. He had this sort of commercial-esque speech that was designed specifically to get people fascinated with having your code in space, sort of thing. And of course, that caught my eye. I'm like, oh, that'd be kind of cool to, I don't really know about that stuff, but I'm interested in it. And so I approached him after class one day, and we basically, at the time, they're doing interviews for people because they wanted to assess the skill level of people before they join the project, so they can, at this point in time, actually, which is in I think late 2017, 2018. The project was already kind of late from the proposal. And so they wanted people to be able to not hurry up, but be skilled enough to work effectively. And so long story short, I participated in a 2-hour-long technical interview. I was actually rejected after that. That felt good. And after that, I started exploring. I really wanted to participate in the project, so I considered working on the ground station, which is basically setting up the hardware to receive and send signals, and even the interface to work with that hardware. But in the same, I think it was the day after that rejection email, Craig, the software lead, came up to me later and said, "Hey, we actually need a Linux expert and then more help on this project. So would you still want to join?" So I was like, no. I was like, yeah. So I joined the project shortly after and started my work.
Cool. So I kind of got the easy way in, honestly. So around the same time Trevor was considered joining the ground station, was the same time I was. But they kind of just decided I couldn't make the time commitment, so I just kind of went on my way. But then I had a classmate who I collaborated with in a class heavily because the class was pretty hard. It was a hardware design class. And he was in charge of the command ingest software for the satellite. And he told me about the project and actually kind of helped them debug some of the code. And so long story short, I ended up going over there, and Craig, the same guy who was in our class, the software lead, he talked to me about joining because Trevor was kind of in there as well. And so Caesar was the guy's name, and he actually had to leave the project shortly after I came on because he was getting busy with classes. So I ended up taking over the command ingest system right after he left. And then shortly after that, we were going into our senior year. So 2018, 2019. And we needed a project for our senior capstone project. And so since the delivery date for the satellite was around the same time as we had to be done with our capstone, we decided to just use that as our senior project, which we did. Excuse me. And so I'll let Trevor give a little overview about the work that he did.
Right. So initially, I'm going into this building. It's called ISTB4, which is basically the newly founded School of Space Exploration at Arizona State. And in the basement of that building is a bunch of labs. And one of those big labs is a big room with a development table and a lot of hardware in it. And this is kind of where all of the magic happened, so to speak. And initially, my job was to get the GPS to work. Basically, it was this piece of hardware that you see on the right, and no one at the time knew how to interact with it. And so my first job was, okay, how do we even talk to this thing? And how do we, after that, even use it? So once that happened, I was able to get it to work. That involved into writing software around this GPS device, the OEM Novatel Novatel 615 GPS. And this involved getting data from it and setting certain settings on it, sort of implementing a fixed set of commands to, a high level set. Okay, I want to get the time. I want to, set this certain setting, that kind of stuff. And after that software kind of was close to completion, we were working with this onboard computer we'll talk about later that was very limited. And so I had to write these certain support functions to convert time structures between the onboard computer and this GPS, because the GPS uses these C structures that are date-based, so month, date, and year, whereas the onboard computer, OBC, uses Unix epoch seconds, so this amount of seconds since January 1st, 1970. Which you can kind of see an example of in the bottom of the slide. I'll go over more of what I did later on, but now I think Devon will talk about a little bit what he did.
So I actually forgot to make a slide for my summary about what I did, but I'll just go over it real quick. I talk about it in detail later, but essentially what I did is I worked on the command ingest system, as I kind of explained before. So basically we need to be able to, from the ground station, tell the satellite what we want it to do and when we want it to do it, such as take a picture over Phoenix. And so what I did was I implemented a system where it would read a file with commands of a certain format and convert those into structures, like C structures, and then send them to a scheduler to be executed by the relevant hardware at the specified time or immediately. I also helped write firmware for the satellite. So before the onboard computer even started, I had to help modify some of the firmware for the startup code in order to meet certain requirements by Nanoracks, who was the organization that we had to deliver the satellite to be placed onto basically to get into space. And so I'll just move on here. So here's a picture of the team, and then. So there's Trevor and I. Here, let me get my pointer out here. So that's me behind, and then Trevor is right here. And then here's our software lead, Sarah, and then Craig, the software lead that we've been talking about. This is him right here. We can kind of see it. We had like this countdown clock back here that counted down to when the launch was supposed to be. And because we had several delays, that got pushed back several times. Okay, so moving on to the overall design. So here's kind of a general structure of the satellite. And so this is kind of standing up, like if you stood a shoebox up. So at the bottom here is the FLIR camera. So this is the, let me get my pointer out here. So this is the infrared camera down here. It's kind of like a barrel looking thing, cylindrical. And then here's the GPS antenna, so the hardware that Trevor was working with. Now, originally we had an S-band antenna on it. This was for downlinking images at a higher rate. But due to complications, we actually ended up having to not use S-band, and we ended up using UHF instead. And so we have a UHF.
Somebody broke the hardware.
Yeah.
Basically, somebody broke the hardware, yeah.
Those dang college students, Anyway, so here we have a UHF antenna up here for both transceiving, I guess, and image downlink. We also have, so here's a bunch of electronics that contain like the battery, the electronic power supply, the onboard computer, the radio. Those are all in this stack right here. And then we have the attitude determination control system, so ADCS up here. And then these 4 little things poking out are the antennas, I guess. And those are deployed when the satellite starts up after it gets ejected from the ISS. And so here's kind of a skeletal view of that, of where all the mounts are. And so let's move on here. So here's a little bit more detailed specs for it. And so a lot of our hardware was kind of just off-the-shelf components, like by providers like ComSpace, ClydeSpace, Novotel, Maryland Aerospace, and EnduroSat. Yeah, I won't go into too much detail, as I already explained, but let's see, what else is new here? Yeah, we don't have an S-band transmitter anymore because the hardware broke for that. Our battery is 40 watt-hours, and our OBC, so our onboard computer, is a Nanomind A3200, which is made by ComSpace. Yeah, and let's see. Yeah. Okay, so here are actual photographs of the satellite. So both open and closed chassis. So we can see the camera down here is this barrel right here. It's the FLIR camera, as well as our hardware stack, and then our attitude control up here, as well as these little antennas poking out. I don't think those are the actual antennas, though. I can't remember which model this is. This actually looks like the flight. This could be the flight model, so those actually could be the antennas.
That is the flight model. So most of those parts are actually 3D printed parts that are the exact specs of the hardware, so we can fit it and make sure everything fits without actually having to take those expensive pieces of hardware and jam them in and say, oh, this doesn't fit, oh, it broke. So these are a lot of the 3D printed parts. But the right is an actual picture of the actual thing.
Okay, gotcha. So if you look at this thing right here, this little tag hanging out up here, that is actually an inhibitor switch. So the satellite is off until this switch is pulled. So right when they deploy it from the International Space Station, they'll actually pull this out. It's kind of like a grenade. They just pull it out and then it kind of starts. And I kind of helped write the firmware to help aid in that startup sequence.
And something else, if you go back a little bit.
Yeah.
On the outside layer of that right picture, I don't know if we have a picture of it in these slides, but there's solar panels that go on the sides so that we can recharge the battery. You don't see them in this picture, but they're there.
I couldn't find any picture of it, so I couldn't include it. But yeah, the solar panels would go on these outside, like the outside of the box, basically. And so we had 2 models. We had the engineering model and the flight model. This is basically 2 copies of all of the satellite hardware that were purchased. This was so that for several reasons. One of them is so we can have workmanship validation in comparison to the project requirements. This was called factory level checkout, as well as for the main reason that we had this is for in order to be able to troubleshoot and test things while the satellite was in space. Because while the satellite's in space and something's going wrong, there's really no way to find out what's going on unless you have a hardware replica where you can re-emulate the problem. And so this was for mainly testing and verifying our hardware, as well as a backup. So we actually had a few hardware pieces break because of some difficulties. One of those was the onboard computer. Our software lead actually shorted that $7,000 piece of hardware on the flight model, and so we actually had to use the engineering model in the flight model after that happened. And so that was a little scary, as well as expensive. And so the engineering model is kind of open and stuff, and so we're able to work with it while we're troubleshooting and prototyping. And the flight model is it was enclosed in a clean room, and not to be touched because that hardware was sensitive for space tests. And so it needed to be clean as possible. Cool. And so here's the engineering model. We called it the FlatSat because, as you can see, everything is laid out here flat instead of stacked up, so we could work with it easily. And so here we have our battery, as well as our EPS, or electronic power supply. We also have I didn't label it here, but these are inhibitors. And so it'll actually use external power instead of the battery for certain things, and in case the battery went bad. And so here is the GPS. So here, this is what Trevor worked with. And then this is the AX100 radio, which is, you can kind of think of that as like the transceiver to the satellite, as well as kind of a router that routes certain like packets to certain pieces of hardware, or I guess to the onboard computer mainly. And so here, right next to it is the Nanomind A3200 onboard computer. And as well, back here is the attitude control system, or ADCS. And as well, you can kind of see here just breadboards for prototyping in between. And I can't remember what this is. I think this is some sort of power distribution board for switching. I never actually interacted with this, so I'm not really sure what that is. But anyway, this is what we worked with basically when we came to the lab and were working on the satellite and doing all the tests. We were interacting with this thing right here. So here's kind of the flight software overview. Everything was written in C, and NASA provided us with their core flight system, or CFS, which is kind of like a library for calling certain functions that just didn't need to be rewritten. It included hardware applications as well as command handling applications, telemetry applications. And the overall vibe I didn't have to actually work with this personally very much, but the overall vibe I got from all of the developers was it was very complicated to work with, and the documentation was just very suboptimal and very just hard to parse and just scarce. There was a little bit of free RTOS involved as well, because we had an operating system abstraction layer, so we could build on Linux for testing and then build for the ARM OBC. And so our minimum functionality was basically just have the satellite take a picture and downlink it. And so that's basically what our finished product did. And so
yes.
This is kind of the topological view of how the software works. So basically each piece of hardware, so like the ADCS, the EPS, and the GPS, things like that, each of them both had a manager and a driver. And this diagram kind of shows you kind of how that works. So the manager kind of receives commands and is sort of acts as a managerial role, and then sends commands and messages over the message bus to the hardware driver, which actually is what it does. It controls the hardware itself. Trevor, did you want to elaborate on that a little more?
So just an example of how this might work is a good example of this is the GPS applications that I wrote. So in this case with the GPS, the hardware the manager application would take so before I get into that, so CFS, core flight system, sends what are called messages between different applications written in CFS through what is called the message bus. And the message bus basically the way that works is it's a pointer to a structure of data in memory, and that pointer gets passed around to different devices. And so usually what would happen is the OBC, the onboard computer, would send a message. Let's say it wants to get telemetry from the GPS, then it would send the corresponding message to the GPS manager app over the message bus. And from there, the manager would take care of high-level things like making sure the parameters were in the right range and making safety checking, that sort of thing, and then pass that message, or actually it would create a new message and send that message over the message bus to the driver app, the GPS driver app, which would actually take care of actually sending the data to the GPS, which actually happened over USART, and then get data back if there was anything that we needed back, and send that as a response over the message bus to the application, the subscriber application that needed the data from that. So that would be an example of how that works.
Right. So just to put it in short, we had to deal with a lot of data transmission protocols. So there's UART, USART, SPI, I2C. We even had to use a CAN bus for the attitude control system. And so it's kind of all these complex things we had to worry about, which made development kind of, we had to read a lot of documentation, and even then it was kind of sparse. And so just a little bit of detail about the stuff that I did. was the command ingest, whose purpose was to translate a file containing text commands into structures the hardware understands. And so kind of as Trevor mentioned, commands were sent over the message bus to a scheduler. So it would read the timestamp of when you wanted to execute that command, and then the scheduler would handle the execution of that command when it was the proper time. So the scheduler itself and CI, the command ingest, were eventually combined in the final implementation. And so this system would validate, before it would execute the commands or even process them, it would validate one that you had the proper call sign for the satellite. And we had some sort of rotating cipher that you had to use. I can't remember if that's still a rotating cipher or even. I think there's more information on the website for how to contact it if you want more information on that. But anyway, you have this authentication before sending commands. And so the kind of flow was, you have this file full of commands from the ground station. That gets sent over the air to the satellite's radio, the ACT100. Then that gets processed by the command ingest system, which sends the commands to the scheduler. And then the scheduler would execute, or I guess send the command over the message bus to the relevant hardware manager, who would then execute the commands through the hardware driver. And so the second main thing I did was I helped to modify the firmware for the startup antennas to deploy. So the requirement stated that we had to have the antennas deploy and the satellite start up at least 30 minutes after it was deployed. This ensured that it didn't take up too much power before deployment, as well as it needed to be far away enough from everything and isolated enough so it didn't interfere with anything. And so I was able to modify the A3200's firmware to wait to deploy the antennas to start up in flight software. I won't bore you with the details, but kind of how it works is basically it tries to do algorithm 1, which efficiently tries to burn the proper resistors to deploy the antennas. And then it checks to see if the antennas got deployed. And if that doesn't work, then it just burns all of them and just like goes full out. It sends the power to just deploy the antennas. And in this picture I have over here circled this little black piece of hardware as well as the breadboard. This black thing is what I use to test the antennas. So there's, if you can see, there's 5 buttons on here. And so I could simulate, when I press those buttons, that simulated each of the antennas deploying. And so I could test to see if it worked by pressing those buttons or not pressing them and see what the firmware did. And so, yeah. And so now I'll let Trevor talk about his work with the GPS a little bit more.
Right. So as I mentioned before, the GPS has a certain functionality that we wish to use with the satellite. So the main functionality that we used the GPS for was getting position, getting time, and syncing the onboard computer's time with the GPS time. And to do this, we sort of implemented an ABI, or application binary interface. Basically, all that means is, okay, the onboard computer expects the GPS to do something with these specific commands, like get time, sync time, that sort of thing. And implementing those functions is what I did with the GPS. Again, the model is the Novotel OEM 615 from Novotel. And the GPS interfaces with a USART. It interfaces over USART. Initially, I would it has a pinout on it, and I would use this special adapter that would attach this pinout and hook into your computer over USB drive, sorry. And initial testing would just be to compile my software on Linux, but eventually the software would have to be compiled on the OBC, which was not Linux. It was a sort of FreeRTOS hybrid thing, and to do that, I would have to actually, there's no USB port on the OBC, so there was this special connection under the board that the OBC sat on, and you would hook it up there instead of those wires you see in the picture. And so, as I mentioned before, the manager app for the GPS would safety check and send the commands to the driver app, which would execute those commands with the GPS, basically sending raw bytes to the GPS and getting raw bytes back and then interpreting those bytes. We would gather and deal with time, position, and GPS telemetry, which is basically, okay, is the GPS doing okay? Extra functions included the sync time function, which actually used the time gotten that was got to sync the OBC time with the GPS time. And this, in turn, called other functions, which converted time between the different, Unix epoch and date structures I'll talk about next. There's a lot of testing that I had to go under the roof of the ISTB4 building so that I could actually see if I could get a fix on satellites and get real data from the GPS that, if you get all zeros, it's kind of hard to tell which zeros you're getting, but if you get raw data, you can tell which numbers are which when you're testing. Want to go to the next one?
Yeah, so just real quick, our lab that we worked on this stuff was literally in the basement of ISTB4. It was like underground. So we couldn't really we didn't have cell phone service down there, so let alone GPS signals. So we had to go to the top of the building, the seven stories, I believe, to get this reading.
Right. And so as I mentioned before, we had to convert time between the time structure you see at the top right. You see that there's seconds, minutes, hours, days, and so on. How do you convert between that and just raw seconds since January 1st, 1970? Now, as I mentioned before, we did a lot of our testing on Unix-based systems that are POSIX compliant, which means they have support functions that allow ease of use. You don't have to write everything from total scratch. You have a little leeway there. However, the OBC is non-POSIX, and so those helper functions aren't really there. And so and that includes the conversion between Unix timestamp and date structures. So I actually had to write that from scratch. And because it's such a small computer, 8 kilobytes of RAM and very limited processing, I kind of had to engineer how the code was written so that it wouldn't take up too much of the CPU's time, because our focus of this function is mostly going to be used to sync time, and we don't want it to be off. So this actually, I tested this a lot with very primitive for loops, while loops actually, in different situations. I basically, the time frame that I knew the satellite was in space, I tested the output of these functions for those times and other times just to get a roundabout test environment for this. And as a side note, in the GPS driver app is where the GPS actually syncs the OBC clock. So the function that's called and is invoked every 6 hours to sync time every 6 hours. So.
All right, so now that we've bored you with all of the details, now we'll go into the actual launch of Phoenix and what that was like to watch that. And so these are actual pictures of the launch. Here on the right here is one that one of our teammates took. So we were about 2 miles away from the launch pad. We actually got the place where we watched was actually the congressional guest area. And so it was pretty close. Over here is actually, it's a funny story. So right after we watched the launch, Trevor went on Reddit and saw that someone had posted this picture of the launch in this incredibly high quality. And so that was cool just to have that. And yeah, I think that's the picture on his phone right now. But yeah, that was really very just impressive, And so more details about the launch is that it was Northrop Grumman did it, and so I misspelled Antares, but the primary rocket was the Antares ICBM, and I misspelled Antares there. I apologize. And then the secondary, so the craft that actually is docked to the ISS is the Cygnus spacecraft. And so it was launched from NASA's Wallops Flight Facility on Wallops Island, Virginia, Pad 0A. So actually the shirt that I'm wearing right here, this NASA shirt, it says Wallops Flight Facility underneath it. I actually got that while I was there. And so launched around 9:59 a.m. Eastern Time on Saturday, November 2nd, 2019. And here we can kind of look at the path. So here is the, you can see it's like, it's not on the mainland, really, United States. It's kind of like on this island on the edge. And so the ISS was actually over around southern Africa. And so we can see that it went up and then kind of went southeast and met up with the ISS there. Around just over, I think it was actually over the Atlantic, not over Africa anymore when it actually met up with it. You can see a lot of water in the shots.
And it took about 2 days to reach the ISS. And
yeah. So here's just a short video of the launch. I figured you guys, after hearing us talk, might want to watch a little bit of it. So I don't know if you can you hear it, Trevor?
No. It's okay though.
Oh, really? Okay. 5, 4, 3, 2, 1. Oh.
Of course.
Okay, it's taking off right now. Oh man, internet. So it's an ICBM, so it took off really quickly. This is my first rocket launch to see, and it was just, I was expecting the big Saturn V, where it took like a few seconds to take off, but we don't live in that age anymore. And so, yeah, since you guys can't really hear the sound, I'll just kind of skip ahead. So it's going up past toward the sun, and then let's see if I can find where it actually turns and goes toward the ISS. Yeah. Might have to.
As you can probably tell, I took this video with my phone from the launch pad.
So, yeah, you can see the fireball from the rocket. So it just turned, and it's kind of going from straight up to turning to go towards the ISS. And so, yeah, and then you can kind of see, oh man, this is terrible. I know I should have plugged in the Ethernet cable. You can see the smoke, and it's on its way to the ISS. So yeah, I'll just stop there and continue forward. So here's some pictures from our trip there. So here on the left is me standing in front of the countdown timer before the launch, so about 42 minutes before the launch. Here's us at the center Wallops Flight Facility, standing by the model of the Antares. Here's Trevor standing after the launch next to the timer. Here's a picture of our badge, and so you can see that it says congressional guest on it. And so the teams that had projects going on the rocket actually got to go to the congressional guest viewing area, which is why we were pretty close to it. And so we got on 11 of these big buses, and it had a police escort from Wallops Flight Facility to the viewing center, which is pretty cool. And here's us standing. So this is what the Cygnus looks like on this poster right here. And Trevor and I are wearing our Phoenix shirts, which has a little blueprint of the satellite on the back. And then here is us standing in front of the visitor center at Wallops after the launch, where we were interviewed by some folks from our School of Journalism at ASU about the project. So it's pretty cool. Cool. So that was the launch of Phoenix. So that was how it got from the ground to the International Space Station. And so here is the deployment. So from the International Space Station to space. And so I'll let Trevor talk about that.
Yeah, so as you can probably tell, that big thing with the huge discs coming out of it on the right is the Cygnus spacecraft, and that little arm on the left is the arm that grabs it on the ISS so that it can pull it in to unload the device, unload the payload. And so you can go through those pictures, Devon. You can see.
So this is arm's going up to grab it. The arm is hooked on. I guess that wasn't quite hooked on. Now it's hooked on.
Yeah. Go ahead. So that gaping hole right there in the middle is actually goes into the Cygnus spacecraft here, and that those cubes that are being pulled out are actually the projects, including Phoenix, that are being unloaded from it on the Nanoracks deployer pod. So Nanoracks is the group at NASA that helps students get their projects actually up to the ISS or into space. So go ahead and go.
Okay. So this video is our team reaction to it being deployed.
9, 8, 7.
T-minus 10 seconds until deployment.
9, 8, 7,
5, 4, 3, 2, 1. Mark.
Where is it?
For confirmation from Nanoracks Teaching Operations Team and Kibo Robotics Team.
All hail Captain Team!
Look at that thing go.
Amazing. It's gone.
Enjoy the view because it's not coming back.
This is the actual deployment. It's coming out of the. Oh, really? I'm able to play that one too? Oh, you gotta be kidding me. I'll have to pull it up on my drive separately. So here's a GIF of the satellite coming out of the ISS. So here's the deployer, like the little cannon looking thing, and then here's our satellite. These are taken on the ISS, and so I'll just play this real quick, and so you can see it coming out, and it's going towards Earth. You can kind of see clouds down there, kind of get illuminated by the sun. So then there it is, kind of going in orbit down there. So yeah, it's just a little short GIF of. So that was actually a bunch of pictures that were taken of it. Just kind of interpolated into a GIF, and so yeah, I'll just move on. I'm sorry, dang it, that sucks about those videos. I'll have to see if I can pull up my Google Drive later after the presentation, if anyone's interested. But I'll just move on for now. And so, all right, so here's our team post deployment, and so on the screen back here is the video that I was going to show that failed to play. So there's the arm, and then the satellite shot out of there, and then here's like more shots of it. So this was actually in ISTV4 at like 2 in the morning because, just the time difference, and so this is at 2 a.m. And so here's Trevor. So here's me, and here's Trevor, and then Craig is not in this picture, but there's our project lead Sarah right there. So it's pretty cool. We got like the theater to ourselves, and we're able to watch the deployment on the big screen. And so it's pretty fun. Cool. And so I'll let Trevor continue with more details.
Yes. So once Phoenix was deployed, we were successfully able to send a schedule file for it. So here we see a picture of a packet that we got back after sending a schedule file to it. You can kind of see the beginning of the text there at the bottom is highlighted in white. Schedule file saved successfully is what that would say. And so that means that the file was successfully received by the Phoenix and saved for later execution. So if you go to the next one.
You can kind of see the call sign right here as well as the cipher.
Yeah, sorry.
Well. These always start the file. So
that would be the call sign of the satellite. Okay, so here we see a bigger packet that is basically the response to us requesting telemetry from Phoenix. I can't remember exactly what telemetry this is, but you can see comma-separated floating point values there of some sort of telemetry. Also, at this point, we are able to hear the health beacon that Phoenix is broadcasting by actually other amateur radio operators all over the world. So that's always good when you can get a health beacon. So after a while, Phoenix became a little difficult to hear from, and so we were trying to figure out why this was. We couldn't really communicate with it too well, and a lot of our communication up to this point were requesting data through the onboard computer. And so one of the ways we troubleshooted this problem was we tried to just directly talk to the radio, the AX100. And we were successful in doing this. And we see the response in this picture. You can't really tell from this picture, but basically we realized that a routing table on the AX100 had been deleted, which is kind of weird, because the routing table is, how it tells the radio where to send things, and if it's deleted, well, that's not good. Now, so the first question you probably are asking is, well, why did it get deleted? Well, that's something that we had to troubleshoot. So if you go to the next slide. Okay, well, we received a successful response when we sent a command to the AX100 requesting a certain value in a certain table be a certain value. We see an example of a successful response to that here, where which is just a response packet to that command. Next. Okay, so project close. Here I'll talk a little bit about what we've been talking about, but so that error state we mentioned before with the table being deleted. So somehow we eventually figured out that the Phoenix had shut down due to some sort of power issue that happened where the battery was depleted. But obviously we were able to talk to it, so the power came back up. And after about 2 months of testing, we revealed that somehow a packet was sent to the onboard computer's FTP port, and this enabled the RDP protocol, which was never enabled in our software, or and the ground station didn't use it either. But the RDP protocol initiates by continuously sending response requests to the ground station, basically asking it to acknowledge the RDP connection. But because our ground station didn't use RDP, this RDP signal just kept sending out, and so the Phoenix just kept sending RDP and initiation packets, and this gradually depleted Phoenix's battery and caused the OBC to now go into the error state, unable to process commands. So it's kind of a catch-22. So the constantly sending out the packets depleted the power, and because the OBC is constantly sending out packets, it's not doing anything else. So it can't, tell the ADCS to orient the solar panels towards the sun to get more power. And so it's kind of an unfortunate situation where we can't really do anything about it. And this was revealed after 2 months of testing that we revealed this limited functionality. This picture here you see here is an example of the start of an error packet. That's all that is. Let's go to the next slide. However, we can still use Phoenix because the AX100 is still able to receive commands and send things. So a possible use case for this would be to help calibrate other two-way communication from new ground stations on Earth, or even to do simple, AMSAT-like messaging through the AX100. So we can't really do science with it anymore through the OBC, but we can still communicate with it, and thus it still can be used for something. That picture you see there is actually the top of ISTB4. That was before, I can't remember when that is, but that dish right there is actually how we talk to the satellite when it is within range. So when it's overhead, we can talk to it.
Is that the one that's on top of ISTB4 that we helped with set up?
Yes. So yes, it is.
Gotcha.
Go ahead and go to the next one. So like I said before at the beginning, there was a lot of stuff on this project that was awesome to learn about. And, Devon and I had never worked with anything that would go into space before, so that was awesome. I think that, working with many individuals on a huge software project like this is definitely something that if you're doing computer stuff, everyone should have to do at one point, because it just teaches you how to really contribute in contribute in a meaningful way, but also not just to personal projects, but also to bigger projects that require many people. Now, one thing that was cool about this is we got to learn how to engineer our code. So having something work on an 8 kilobyte memory machine that isn't even a architecture that you're familiar with, but also making the code safe so that no segmentation faults happen that crashes the whole computer, which was actually required a lot of bit of testing on our end to make sure that this didn't happen. We also had to work with hardware that didn't really have that good documentation around it, and so we had to work with companies to figure out how this hardware works. And a lot of the hardware was pretty expensive. The GPS was about $3,500. The OBC was $7,000. And breaking that hardware is unfortunate, but also kind of interesting at the same time. So the GPS, I actually was able to let out the magic smoke, so to speak, on one of the ICs on it by accidentally plugging in power to a 12-volt pin where it only requires 3.3 volts. And anyone who's ever done anything with embedded electronics knows that definitely will let out the magic smoke. And so we had to, luckily, unlike the onboard computer, we didn't have to replace the whole thing, which would cost $7,000. So much so that we didn't actually replace it. We just used the flight model. We actually were able to replace that specific IC on the GPS for only like $300. Another thing we were able to do is learn how satellites work. Devon and I are working with computers. A lot of our background is software and hardware, but not anything to do with real space stuff. And so being exposed to that was real cool for us. We're going along with a huge project like this, especially with the software. Just being able to accommodate the continually changing demands of the project. Consistent code refactoring was something that we constantly faced, especially me. You see here, I mentioned a thing called issue 45. So the background about that is, towards the beginning of the project, I had finished a lot of the functionality for the GPS software. And anyone familiar with GitHub or GitLab knows what a merge request or pull request is. Basically, that's requesting that your functionality be integrated into the main code. That didn't happen with this issue because of so much of the demands, the requirements of the code being changed. Oh, and I had to constantly rework the code to do it. And issue 45 was actually never merged back in, but I was able to create a new issue later, about 5 months later, and get that merged in. So, like I said, there's a lot of moving parts when you work with a lot of people, and we definitely experienced that with this project. But it was a cool learning experience, I would say. And that was only a few of the learning points that Devon and I experienced. That lower right picture is actually the first picture of the team taken by the FLIR infrared camera. Yeah, Devon, go ahead. You want to?
Yeah.
So yeah, that's basically sums up our work on Phoenix.
And yeah, and there's definitely more details about the mission on that website. So phxcubesat.asu.edu. If you go to that website, there's a lot more information you can find about the project, and if you're interested in communicating with it. Thank you so much for everyone that stayed with us this long, and I know it's past all of our bedtimes and all that, so thank you guys.
I'm muted.
Okay, well, I really want to thank you guys for this presentation. And does anyone have any questions out there? If you have any questions, go ahead. You can either use the little chat feature on the right-hand side there, or you go ahead and just post your question. W2VX, Doug, you're posting up a thank you sign. Kudos all the way around there. Do we have any questions for Devon and Trevor?
I do, George.
Go ahead, George.
What was the budget you had What was the dimensions of the unit when it was launched, and what did it weigh?
I'm sorry, could you?
Yeah,
repeat that
so the question was, what was the dimensions of this of the CubeSat, and how much did it weigh?
And what was the budget?
And what was the budget?
Good question. I'm trying to remember. That was how long ago, a lot of that stuff. So the dimensions, as far as that, so 3U, I'm trying to remember the dimensions of 1U, but I can kind of picture it in front of me. It's about, let's see, about a foot and maybe a foot and a half long, and about, I want to say, 5 to 6 inches square. So for that square, it's about five inches on either side, and then the length of that is about a foot and a half.
That's what Greg has 3 times.
Yeah, it should be 4 inches on a side and weigh 1 kilogram. Although the weight, I'm not sure if that's changed over time. So this is a 1U. You stick 3 of them end to end. So it's be 12 inches by 4 by 4, I think.
As far as the budget, I actually was never really involved with the budget financially, with that side of things. But I did hear a lot that we, especially after we broke several pieces of hardware, we kind of had to not be able to replace anything anymore because we kind of ran out of funds towards the end. But I can tell you that much.
Okay, very good.
I can't remember.
Any more questions?
Hey, this is Philip, KM6NFS. Quick question about the onboard computer. If I was to compare that to if I was to compare the spec sheets of that to the spec sheets of a Raspberry Pi, what kind of differences might I see?
All right, yeah. So I can tell you that some of the things that might be the same as the CPU architecture. They're both ARM based, and so that was, I guess, consistent for people that develop with Raspberry Pis. But the memory was pretty limited. It's a very even more embedded than the Raspberry Pi. So usually, I think the modern Pis even have 8 gigs of memory, or they used to have like 4 and then 2 and then 1. But I think ours had around 8K, Trevor?
Yeah, it was 8 kilobyte of memory. And actually, one of the problems we had was because the software is continually running nonstop, and so we had to really figure out. There's some parts of the code that had memory leaks, and if you have a memory leak constantly, that's going to overflow your memory, and so that's one issue that's why we really have to look over the code and make sure that it's we have a lot of safety checking in it,
as well as the stack size for function calls. As far as ports, I think we had a what was the cable we had to connect to it to flash it? I think it was was it over serial?
It was it was some sort of serial
TDI cable, I think. So it's not like a Raspberry, the I/O isn't as like a Raspberry Pi where you have like GPIO, USB, aux, things like that, of course, because it's an embedded system. But I hope that I answered your question.
Yeah, it did. Very cool project, guys.
Well, thanks, you guys. Great presentation this evening, and we just definitely wish you guys the best in your careers. And what a great opportunity to work with some stuff that we, the stuff is floating over our heads. We have sometimes no idea what went into it or what's going on with it. And thank you so much for kind of giving us that inside thing, and what an opportunity you guys had. So thank you so much, and hopefully we can have you back again someday to talk another project, and the best of luck as you guys find your way into your professions, and we look forward to following you guys. So thanks a lot.
Thank you, Brian. Appreciate the opportunity.
Yeah.
All right.